So now, first we will talk about how to use TensorFlow for your TPU environment. Okay, so this is very important for your TPU cluster. If you want to use TPU cluster, so basically for your collab, you can go to your runtime and change runtime type to your TPU. Okay, as simple as that. So basically, by default, 8 TPUs will be available for you, and you can use that. Now, how you can use that, and we will use that with different strategies. Okay, so basically, XLA mixed precision, TF function runtime, and so on, distribution strategy, blah blah blah, right? So let's see all of them in one place. Okay, so importing the things here. So all the things are imported, and then you just see which profiler, which TPU version is being used. We are just printing here and using AutoTime for time displays. Just a few libraries. Now checking if TPU is available and changing the runtime to your TPU. So basically distribute.cluster resolver. Yes.
Sir, they can't view the text properly, so requesting to increase the size.
Yes. So I hope this is visible now. So till now, whatever we have talked about is basically the imports and setup. Okay, that is very simple. But now what we are going to see is that how to define the how to use the TPU for your devices, target device, and distribution strategies, and so on. So we are defining the resolver, how we are defining here TPU cluster resolver that we have seen in the previous class, experimental connect to cluster, we are connecting it, and then TPU initialization code, right? So to just at the beginning, you need to initialize your TPUs. Now, by the way, XLA is very good for your TPUs, okay? Because many fused operations that the XLA will generate is directly supported onto TPU, because TPU is basically from Google, TensorFlow is from Google, XLA is from Google. Now you connect everything. Okay, we will see what kind of performance we are getting here. TF function, JIT compiler equal to true. So this is how we'll enable here. Now, first we are just wrapping up, warming up with some function. So this is one function that we're going to reduce. So basically, this is the graph, computational graph, and we are running it with the TPU. That's it, right? So all the TPU information you are getting, and then you can see the runtime here, and the strategy that we have defined before, right? So the strategy you have defined here, distribute strategy for your TPU, and we are using that strategy for running this particular function that we have created. So this is a very simple example how you will actually create the strategy, enable the XLA compiler, and run it. Okay, but let's take a concrete example for model training where you will apply all this. So basically here, what you are seeing that all the necessary imports and version checking and blah blah blah, that is fine. Again, TensorFlow import for the data set, because we will use TFDS for importing the data sets. Whatever the data set that we want to load here, we are loading MNIST data sets, splitting train test and shuffle true, supervised true, all these things we are setting up. Good. Then we are normalizing the data and setting up one input pipeline. So that we talked about previous section also, that map is basically transformation with this normalized function, right? And number of parallel calls, we are letting how many number of parallel calls that will be generated. ds.train, we are getting the cache enabled, shuffle, batching, prefetching. Everything is there. So you now know how to do that. Now build an evaluation pipeline. So basically just checking here and creating the model here for the sequential model. Simply we are creating 3 layers of model 1 flattening layer, that is just taking the input and flattening it. 2 dense layers are there, and this is the output. Output of that is softmax function. Okay. So model.summary, as you can see here, we have 3 layers here and the summary. Now, at first, just to see how it is performing, we are setting the tf.config.optimizer.setJIT is false. This is another way to set JIT compiler equal to true or set JIT compiler equal to false. So we are disabling the XLA because we have enabled previously for that toy example running. Then model equal to compile. So basically we are compiling the model, and now we are creating the training pipeline for that, and we will be using, since you can see that here we have generated the model using the sequential API. So it is I mean highly likely that you will use model.fit. Okay. So but as you can see here, as tf.function JIT compile equal to true is essentially trying to make the computational graph, and model.feed is actually, again, you are doing that. But that means tf.function runtime is not supported for your model.feed. So if you are using model.feed, we will not be able to enable the XLA. So just importing the TF and blah, 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 data set, and running the resolver, initiating the devices, right? So all these for TPU that you have seen so far, just getting some data about the image size and image classes. You can see 60,000 images up there for your train, and test data is 10,000 and so forth. And then this data input pipeline normalize, which is used in map, again cache, shuffle, repeat, batch, prefetch. And then we are building the evaluation pipeline now. So basically calling the functions here, again using the tf.device. But here now we are enabling the JIT set JIT equal to true. So if you see the earlier training for that matter, so if you see here where we are actually using the modeling, okay, so where we have repeated, yeah, okay, so okay, so this is the model summary, and yeah, so set JIT true and compile, and then we are using the distributed strategy, okay, TPU strategy, because we want to distribute for the TPUs that is available here. And thus inside this strategy scope, we are defining the model sequential, and after that we are generating the model summary and setting up the compiler here, okay, XLA true. Now you can see total TPU cores are 8, and TPU workers is 1, and you can set it like how many workers you want. You have seen in the previously how you can configure those scenes. And then model summary you have seen, and then we are fitting the model. So the model fitting is essentially running the model for your generated graph for that, and you are using that, and total of 16.8 seconds you are spending for your training of 2 epochs. Now we are moving towards the example where we want to enable the XLA, but with the TPU and also with tf.function runtime. because the TF function runtime has its own optimizations that you have seen, because it is serializing the computational graph. That is not possible for your model.fit, and that is why the performance was not that good. Simple. Now, the same setup, importing the TensorFlow or all the data set libraries, then initializing the resolvers, right? And something regarding the data, and setting up the just viewing the data frame. Also, you can see these are the handwritten dates images from the data set itself, and then setting up the input pipeline, data input or data loading pipeline for normalizing, mapping, caching, shuffling, batching, and prefetching. And then with this device, so one TPU device we are using, again, you can also use any other strategy also. So sequential model that we have defined for that device, and then defining the optimizer and loss function. But now we are actually defining the training step, but not using the model.fit. And we are wrapping it with tf.function runtime with JIT compiler equal to true. And after doing that, we are actually calling the train step for this number, same number of epochs, because we have run for 2 epochs previously, and 4 times speed up that we talked about in the session. In the slides, you can see 4 times speed up you're getting, right? So this is a very simple example where you can set up your own pipeline for your training, and you can define like which exactly steps, which are the steps that will be wrapped with your training tf.function runtime with JIT compiler. And this is one example where we have run in TPU. Okay, now we can extend this for running it several TPUs and see what are the strategies supported for XLA compile, and play with it. Okay, so this is where your exploration for different strategies and whatever methods that you have learned from this course will apply, right? So you take this code and play with it, right? You can also use Keras dataset and see what happens for the particular example that we have seen, because we have used TFDS, the TensorFlow dataset, and try to use Keras dataset and see what happens. Okay, so explore all these things. You can note it down, and you can explore this, because a lot more interesting things that you can discover. I'm telling you. Okay, so let's go into the GPU now, right? So we have seen the TPU part where we have enabled the TPU execution, set up the environment, and wrap the function with the tf.function wrapper JIT compile true. Now we will train first one naive way, because we want to see what is happening here with the GPU. And of course, without MP, the automatic mix precision, without XLA, without anything, it's vanilla training model, right? So where you have this TensorFlow imported, the image, the same thing that you have seen in the TensorFlow model. So same training module here. Train set, test data set, we are unpacking it, model defining with the sequential API, model summary we are checking, and then clearing the session if we have, let's say, running previous JIT compilation session is already on. We are just doing it just for safety. We are clearing the session and setting the XLA disabled. Model.compile will compile the model, training model with this fit function, right? So that's it. That is the vanilla training for the TensorFlow particular pipeline. So interestingly, your DL prof will figure it out that you're actually not using XLA, I think. I don't know. So we'll see. I hope this is the profile for after training with this. So basically, you can see if AMP was not enable it, GPU was not greatly used, and so on and so forth. Unable to split profile into training iterations. So, okay, that's okay. GPU memory is underutilized. That is fine because of the very small model, right? And all the operations that are being actually called and executed, how many times of uh, uh, operations execution call, and how much time you have spent for those operation call, that you can see profile it here. And you can see few of the operations that are matrix multiplication operations, which are actually tensor core eligible or not eligible. So whether using tensor core, no, we are not using, because we are not mixed precision. And all these profiles you can get it from, right? So okay, so just to see, this is very naive way of setting things up, right? Now, of course, average time you can see 12.8. Now, of course, we want it accelerated, right? So let's see what happens if we enable the XLA, right? So the same thing, same training, the data set, unpacking, model definition, clearing the background, and here we are actually enabling the XLA, and then model compile, model train model with fit function and train model. So this is a simple same, just with 2 lines of code, we are actually enabling the XLA. So let's see what happened here. Average runtime got reduced to 7.75. That is good. And but still, so if you see, of course, AMP was not used, and GPU is underutilized. That is understandable. And of course, again, you can see the functions that is, and also you can see which is the operation that is being actually run by your optimized code. Okay, so for the from the XLA part. I have not shown other views. You can explore those. So as I was mentioning, that it is not possible every time to go to every tab and explain you everything, but you can explore the other views as well. Let's say you want to see the operations and kernels that are being executed. You can see the list of the operations and all the statistics behind those. You can export them in PDF, CSV, JSON format, or Excel format, whatever you want. Kernels by operations, iteration, kernels by operation, iterations. So all the things you can explore from this profiler, right? But of course, this is where you will explore more. Okay. Now we want to introduce AMP also and enable XLA at the same time, right? Now we want more performance. We do not know what will happen, right? But we are just we know that if we enable AMP and use mixed precision, then we can, you know, use the tensor cores more. Okay, we can increase the utilization. So let's do that. And also let's keep the XLA on, right? So I don't know what will happen. So let's see eager execution. So enabling the eager execution here. The image size, so all the images, train test data set unpacking and definition of the model work summary. And here we are enabling XLA also at the same time. So in the previous example, in the prior class, that you have seen how we are getting more utilized tensor cores by using mixed precision in our PyTorch class. So extensively, we have not used mixed precision in TensorFlow, but you can use that. How you can use that? Here with optimizer, basically you can scale it, right? So experimental.enable mixed precision graph rewrite, you can enable that for this optimizer, and you can use that optimizer inside your model and train that model. As simple as that. Use mixed precision. And let's see what happened here. And oops, our average iteration time got increased. So that means we have degraded performance. So that means uh, introducing everything, XLA, mixed precision, everything in the tensor processing unit, which is the TPU, you are getting much more performance, right? And that is because that is because Google. Okay, so basically Google supports the mixed precision binary fusion, which is supported in TPU but not supported inside your GPU, and you will not get tensor cores utilized. So still your GPU is underutilized, and whatever XLA run you have defined, it is not using the tensor core, but uh, uh, some of the in the cluster 5A XLA run, this 200 is using the tensor core. Okay, so some parts will not be actually compatible for your target GPU. So you just need to use some libraries. So now here we are using the AMP library from Google itself. Again, you know there are two libraries for that. One is NVIDIA Apex and the native library from PyTorch, both from PyTorch and the TensorFlow. Now you can know what we'll use for getting enhanced performance, right? Now, in the next setting, we will see how you can actually also enhance the training pipeline with TFDS, right? So we will now formulate the pipeline with TFDS, right? As we have seen in the TPUs, right? So training data with TFDS.load from MNIST, splitting training test, and comparing and formulating the pipeline here, and then map, cache, batch, prefetch, sequential model definition, model summary, optimizer, and mixed precision enabled. Sparse category loss we are using here from the logits that we are getting from the last layer, and defining the train step with runtime function, tf.function runtime JIT compiler true. With this, we have wrapped this function, and so I don't know everything we are using here. So the tfds data pipeline, the JIT compiler for the function training step, and mixed precision, caching of data load. I mean, I don't know what else we can have here, right? So let's see the DL block. Okay. So with enabling XLA, we will not give you always the best performance that I have told you in the slides, right? So that is exactly what we are doing here. 12.8, it is not exactly what we want. So if you blindly just enable everything, that does not mean that you will get the better performance. Conclusion is, you see, analyze what is best for you, and actually what you'll get from the exploration and profiling. So use the profiler always, like how you can actually see where is the performance you are going to increase or decrease depending on which strategy you are using. So all these are basically exploration based, okay? And for your target GPUs, for your target TPUs, what will be the best for you? You explore that and see what actually fits for you, okay? What are the optimizations that are good for your target architecture? You explore. You explore this the kernels here that are being generated, and see what kind of fusions you have after the training. You can inline the you can inline to see the intermediate IR as well. So I have shown you in the class slide that what are the techniques for enabling the optimizer graph for generated. So you can use this and see what kind of optimized graph you see. So with this, we'll conclude the session, and thank you for that.